Okay, kids, ready for Stokes Theorem? Stokes Theorem is pretty fascinating and pretty handy. I think you're going to like it. And it has a lot to do. It kind of brings together a bunch of stuff that we've been doing in chapter 16. So it's kind of like the culmination almost of chapter 16. So I want you to look at this surface here in space, and it has a boundary curve, C. Right? Here's the boundary curve C, and I'm going to say that I'm going to travel around this in a counterclockwise direction. And I want F to be a differentiable vector field, just meaning that I can compute the partials of its components. So you need to imagine that the vector field, right, is swirling through here, right? Right, swirling all around here, doing some kind of stuff is all what's happening here. And right, we want to talk about the circulation as what's happening to this vector field as it relates to our surface. What's going on our surface? So what Stokes said, pretty sweet mutton chops there. What his theory states is that if you want to find the circulation, the line integral that is the circulation, right, which is along this boundary here, what's happening along our boundary as far as a normal, right? If this is a normal here, and I'm going along the curve, but the vector field is causing some kind of circulation, right? Maybe it's counterclockwise, maybe it's clockwise, I don't know, but something's happening. And I want to find that at each individual point and then sum them up. Stokes proved that that is equal to taking a point on the surface with its normal, with the vector field creating the circulation here, again, maybe clockwise, maybe counterclockwise, finding all those in the interior and adding them up. He proved that those two values were the same. Now, if you look at your book, oftentimes your book doesn't have this .n. It considers that ds is a vector, kind of like dr, right? It considers d little s as with a vector, but I like the notation of making sure you understand that we are doing a dot product of the curl with the normal. So I kind of separate it out that way. Just don't want you to be confused if you're looking at your book. So Stokes, thank you very much. Gift 1 from Stokes. The line integral is the same as the surface integral. So his first gift is that you get to make a choice. You get to decide, depending upon what your boundary C or your surface S or your surface S, your boundary C, or your vector field is. The math involved in doing a line integral versus a surface integral, you get to look and say, I think this would be easier, so I'll do this one, right? That's gift 1. The total circulation around the boundary, that's the left side of the equation. This is the total circulation around the boundary. Is equal to the sum of all the teeny circulations on the surface. So here is gift 2. Bet you weren't expecting this slide, were you? Gift number 2 is a hat. And what do I mean by that? The shape of the hat, the 3D surface, what's inside that line integral is equal to the surface integral proof, is that the 3D surface is not important to our calculations, just the rim or the curve is, or the boundary. What that lets us do is take a lot of 3D situations and turn them into 2D situations. So here is my hat with a rim, right? Or the brim if you want. The red portion of the 3D portion of this hat, I can squish and move and dilate and pull wheel, I can grab this and pull it up. I can grab a side, pull it over here, as long as this boundary stays the same. The boundary is the important piece, right? We still have to do our line integral, our f dot r or our curl dot n, but with the math, it is the boundary that's important. So oftentimes I can take this 3D surface and squish it, right? If I can choose any surface, as long as I keep the boundary the same, why wouldn't I choose a flat one, right? Kind of cool, kind of cool. So I've left this URL here, and it takes you to this site where I think this is a nice visual of, here is a 3D surface, obviously. Here's the boundary. As long as I don't change the boundary, the line integral and the surface integral, I do that math, will be the same. Notice that I'm oriented outward, my normal, right? If I travel along the counterclockwise direction by the right-hand rule, my normals will point out. If I travel in a clockwise direction, going this way, my normals will point in and I'll be oriented inwards. I do have to have an orientable surface, right? If I change the brim, right, the boundary, that does change things. But again, once again, I can pull my surface way up. I can make it flat, push it way down. Doesn't matter. Kind of cool. So I kind of skipped over this part. Compatible orientation with the right-hand rule. That just means that your surface is orientable, right? You don't have your Mobius strip situation that no matter what point I put on this surface, right? As long as if I'm traveling counterclockwise, I'm oriented outwards. Or if I travel, oh darn it, I still want to hide it here. Clockwise, right? I would be oriented inward or down. So let's use Stokes' theorem to evaluate a surface integral. I am asking you to evaluate a surface integral by the directions. Stokes, though, lets you choose whether you actually want to do the surface integral or whether you want to do the line integral. So here's my thought process. Here's what I think. Because of Stokes, here's in my thought bubble. Can I easily parametrize my boundary surface situation? Is curl simple? Should write easy. Parametrize easily. Calculate curl simply. Those are the things that I think. Now, when I look at my vector field, the curl, simple, right? Curl is not going to be a difficult thing. Also, parametrize my surface, not hard to do, right? Right? So in this case, I don't really have to switch, but so I want to show both ways. I'm going to use the fact that the surface integral is equal to the line integral. I'm going to say I choose not to do the curl. I'm going to do the line integral instead, even though I was asked to do a surface integral. So what that requires is that I parametrize, right? I need to parametrize my surface and plug in to my vector field, right? But that's not too hard to do, right? What would R of t be? So I have a hemisphere. right? There's kind of my hemisphere. So this is my 3D piece. And the blue is my boundary. So parametrizing that circle, wouldn't I get that just cosine t in the x direction, right? Just my circle, and sine t j plus a height, but here's gift 2, right? Gift 1 let me do the line integral instead of the surface integral. Gift number 2 lets me say, you know what, height, don't care about you. I don't care about the 3D piece of this, so I'm just going to say plus 0k. Do my derivative. Even if I hadn't said 0k, right, I am just rising up, right? Oh, sorry, I was thinking about another problem. 0 times k, that looks like okay. Okay. So now I'm going to integrate. And I'm going to take f, right? Where's my vector field? And I'm going to put r of t into it. So I've got y negative x. I guess I could kind of drop the zeros at this point, but just for emphasis sake. I have z, but we're going to say z is 0, right? Dotted with of course, the derivative of 0 being 0. And what do you think I should, right? Going 1 from the start of the curve. I want to start the curve at some, right, and end at the same place. So hopefully you're okay with that 0 to 2 pi. And when I dot all this, I get 0 to 2 pi. I get negative sine squared and negative cosine squared. So factor out the negative, and I have sine squared plus cosine squared. And I get negative 2 pi. Right? Not so bad. Again, what made that easy is that I was parametrizing really just a 2D, thank you, Stokes, I'm so stoked, 2D boundary. And it was very easy to parametrize, plugged it into my vector field, dotted with the derivative of r. Very nice calculation. Now, again, as I said, this one isn't so bad to do the actual surface integral as I was asked to do, right? So what do I have to do for the surface integral? First, curl. And hopefully you can see doing, right? What do I have? Partial z, partial y, partial negative s, partial z, partial z, partial x, partial y, partial z. Oops. But partial negative x with respect to x, and partial y with respect to y. So there's my curl. And then remember what a freaking pain in the butt getting the normal was, right? Getting the normal was, oh, get z by itself, 1 minus the square root of, 1 minus x squared minus y squared, make z equal to 0, call that f, do the partials. Oh, I've got, 1/2, bring down the 1/2, copy over the middle, minus 1 is chain rule, blah, blah, blah. And we ended up with all this stuff that we did get some things to cancel out and all that. I showed you that in the last live session. But remember the hat, right? Stokes with his hat. I really don't care about 3D. I only care about the brim. So remember, I've got a hemisphere. The 3D piece is there, but I want to take that hat and push it all down and flatten and make this a flat surface. So if I make this just a flat surface, what is the normal from that? As you're traveling around, what's the normal? Hello, unit vector in the z direction. Thank you, hat. Right, so now I'm going to do curl, and notice that this, right, change in the surface area, which is a 3-dimensional thing, I now can change into a 2D region, and I am dotting the curl with the normal dA. So I'm just down in 2 dimensions. When I do this dot product, I get just -2, osmosis that out there, and I just get dA, and I don't really need any limits of integration because, hello, I am just doing the surface area of that circle. What is that going to be? Pi r squared. What's my radius? 1. So my double integral is pi, and you're multiplying times -2. So you get the same answer as before. Oh, snap. Thanks, Stokes. Now, let's do this example. This example, if I'm prompting you to use Stokes, I know I did in the previous one, and we ended up doing, right, both the line integral and the surface integral, and both of them were pretty easy to do as long as you remembered all of Stokes' gifts. But if I, on an assessment, say use Stokes theorems to evaluate a line integral, that's a clue that probably your curl is simple. So look at your vector field. That curl is going to be pretty easy to calculate. Now I have 2 shapes here. This is easy to parameterize, and I need the intersection. So I have I've got some cylinder here and some plane coming down through it, so that my boundary, right, they're asking me for a line integral of a, right, of a curve. My curve is here. This is a terrible, terrible representation of it, but right, it's kind of like this elliptical looking thing. There's all kinds of 3D surfaces that might be associated with that, right? I could think about, like kind of like a chia pet, right? Right? Like I could, from this, right, I could draw all kinds of, something from this surface. But why would I want to? Why would I want to? I want to do this line integral, but the line integral, it looks like it would be difficult to do. So I want to do a surface integral, but the surface I'm going to pick is the flat one. It's a flat one. So the surface integral is equal to the line integral. So I'm going to do the curl. Forgot to say I'm so stoked, right? I'm not going to do the line integral. I'm going to do the curl. And hopefully it doesn't take too much for you to see that my I component, my I component's going to be 0. My J component is also going to be 0. And my K component is going to be 1 minus negative 2y. And then what are we going to do with the normal again? Right? You're going to think about projecting this down onto the 2D surface. What do you get? Right? And the normal from that, hello, 0, 0, 1. So my surface integral turns into a regular double integral dA. And I have 0, 0, 1 plus 2y dotted with 0, 0, 1. Hopefully you can see that as just 1 plus 2y. Since I am dealing with this circular region here, I am not going to turn dA into dx dy or dy dx. What are you going to do? Brr, feel a little chill coming. Polars, baby. Pay my price. I am going all the way around, so theta goes from 0 to 2 pi. And my radius was 1. And again, hopefully this isn't too bad. And you can verify if you want by doing that integration that what I ended up with was pi. Crazy, right? So stoked. Way easier than I thought it was going to be when I first looked at this problem. So this was a case where I asked you for a line integral and I wanted you, and it was easier to do the surface integral. This time, this is more like the two problems that I'm asking you to do associated with this video. I'm going to ask you to do the curl, but since I'm saying use Stokes, probably what's going to happen is that this is going to be easy to parametrize, and curl not as much. So look at the curl here. Doable, but kind of gross, right? So they're asking me to evaluate a surface integral. So they gave me a 3D surface, part of a sphere, which is here, that lies inside the cylinder. Look at my boundary, though. Remember that. Stokes has two parts of the presence. Part one is I was asked to do curl, and I'm so stoked because the surface integral is equal to a line integral. Woohoo! Not going to do the surface integral. I'm going to compute a line integral because I can easily parametrize. So first I do have to think about, well, I do have an intersection here. So my z, right, cancel, 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 cancel. Z squared is equal to 3. Z is equal to, since I'm going up, positive root 3. So let's parametrize, right? There is my vector field. Oops, that should have been black there. Didn't notice that before. Be consistent. Look what I did with my parametrization. I should have done that in blue. Right? The projection, right, going around here is cosine t plus sine t. Right? I have a height of root z is root 3. That is just a circle. And that cylinder had a radius of 1, right? So that's why I have 1 cosine t, 1 sine t, and no height. This was the hat. Allows me to ignore the height of my surface. Now I'm going to take my r of t and put it into my vector field. X times z. Z again we found to be root 3. Y times z. And then remember, we're ignoring our height. Plus my hat. That. It looks like that. Now I'm going to dot f of r of t with r prime of t. Hey, you notice what happens there? Oh, I meant my hat to fly up way sooner than that. Gosh darn it. So certainly going around once is 0 to 2 pi for my t's. But notice what happens when I factored out my, oh, I forgot to write it in. I factored out my root 3, so it's out here. But notice what happens to my integrand. That cancels out, so you're multiplying root 3 times an integrand of 0. And you integrate nothing, you got nothing. If you got nothing, 0 to 2 pi is nothing, times root 3, nothing. Okay. So in our, again, in the I only gave you 2 problems to do, and the 2 problems that go along with this video are ones like I just did, where I'm asking you to compute a surface integral, and I want you to do a line integral instead. Don't forget, that's the first gift of Stokes, that he lets you do the line integral instead of the surface integral. And the second gift of Stokes is the idea of the brim, right? The boundary being the important piece. So let that help you in the math, right? By eliminating and pushing the surface down, right? That height of root 3, I push down to here. Okay? I will see you in our live session.